So what's similarity? It's difficult to define. We had to fight to define, for example, similarity among paths, because it's difficult to say if /user /local /lib is more similar to /user /lib or to /user /local /doc. Try to figure it out for yourself. It's not easy to express the reason why your brain tells to you, experienced Unix administrator, that /user /local /lib is similar in function to /user /lib. Anyway, our clustering process aggregates similar uses of system calls. Let's take a simple example. FD format, very simple program, does very simple thing. These are the first few uses of the open syscall in FD format. What happens is that if you run a clustering algorithm, first thing that happens, the first bunch of calls is clustered together. Because if you see it, they have the same path, they have very similar names, and moreover, they have the same opening modes. Here they are expressed in a very curious way, but it's the way we like to read the output of the algorithm. Then, if you run again the merging algorithm, these two calls are merged together because they are similar. /devices, /pseudo, similar. Notice that at the third step of the merging algorithm, this one, which is slightly different from the former ones, gets clustered together with the library's opening. And at the end of the run, we have that. We have three clusters, one cluster with the opening of devices, one cluster with the opening of libraries, and one cluster with just one opening, which is the opening of a terminal character file. This is interesting because it creates submodels for different uses of open. So now we don't have open anymore. We have open1, which is the open which opens libraries, and as models tuned to the opening of libraries. We have open2, which is the open which opens devices, and as models that are tuned to the opening of devices. So if at some point in the open that usually opens a device, I will see an open of a file which does not mean anything in that context, I have much better possibilities of detecting it by using a subcluster of open than by using everything else. So we added a Markovian model. This is not very interesting per se because it's already been done. The model can be, it's a simple first order model, can be trained easily with very few runs on regular programs. What happens is that some researchers suggest that one of the ways to create an anomaly detector is to statically analyze program paths. So you pick up the program code, you statically analyze which system calls can be called in which order, and you build the graph. This is wrong for two reasons. First reason is, if there's an error in that, you will just bring it over to your anomaly detection scheme. Second reason is that this does not generate to you probabilities of executing a particular path of the program. Because one of the things we are interested in is that some users or some systems may use just a subset of the capabilities of some programs. So I may be interested in the fact that a program is executing a path which has never executed before. So at runtime, our model gives out 3 different outlier indications. First outlier indication is how likely is the sequence so far. So I'm executing PS, I run it, I see the various system calls that are generated. For each system call, I execute the analysis of the arguments. I classify it as one of the types. I see the point in which I am in the graph, and I calculate the probability of the sequence up to this point. So this tells me how likely is the execution of the program until now. Second point, how likely is that this particular system call follows the particular system call that was here before? So how likely is the last step? This is a punctual indicator of when a program gets diverted. Third indication, how similar is this system call to other system calls of the same type? So I have a couple of punctual indicators of anomaly which should help me detect the attack in the moment when it happens, and at least one global indicator of anomaly, which even if I don't understand the exact point where my program gets diverted, after a while that my program has been diverted and is behaving in some other way, it gives me an alert that it's not executing in the same way it used to. So, at this point of presentation, many colleagues will give you the results and will tell you, well, my system detects 99% of attacks on the blah, blah, blah data set, and with a false positive rate of 5.2%. I like Dilbert. I think that Dilbert explains many things in information technology, and that strip of Dilbert is particularly enlightening. Dilbert, do you have the benchmark results? Do you want the 10-minute explanation of why this data is useless, or a simple, here you go? Amin says, here you go. I have presented at BlackHat Federal, and you can retrieve it on BlackHat website, all the reasons why most of the evaluation of intrusion detection systems, up to and including the DARPA intrusion detection system evaluation dataset, are useless, or mostly useless if you want to quote the Galactic Guide. I won't claim with you the false positive rates or false negative rates of this system on the DARPA dataset. We evaluated it on the DARPA dataset, of course. Everyone does that. The problem is, if you pick up the host-based data of the DARPA dataset, which is a set of BSM Solaris audit files, I can bet with you that I can write a Perl script or a Bash script or a Python script that detects all of the attacks with 100% accuracy and 0% false positive rate. Why is that? Because every single one of those attacks is a buffer overflow. And every single one of those attacks begins with a very long string being used in a system call. So if you just detect all the strings longer than 300 bytes in system calls into that data set, you will find every single attack with a 0% false positive rate. That data set is useless. If you see each single anomaly detection, misuse detection, IDS paper in the world uses that data set. So it's not like I don't have the results. I do. if you go and look up my doctoral thesis, you will find the results on the DARPA dataset. But it's useless for me to show them up to you, because in the real world, everything will be different, right? So what can I say instead, qualitatively? I can say that my system can contextualize deviations. So whenever you find out that a program has deviated, you have a very good guidance that tells you exactly in which point the anomalous execution began. Second important result is that using the clustering of system calls grants a much better granularity and makes it so that the system on real-world examples behaves so much better than competitor systems, which are instead based on just the type of system call. Why is that? That's because the DARPA evaluation dataset is 1999 or 1998. It's been an age. They use mostly interactive software programs run on the common shell, not daemons, not servers. So what happens is that in a program which executes on the common shell, it's not really important if you have an open of one type or open of another type, if the buffer overflows is always present in the first parameter of the open system call. So I concluded my talk. I tried to argue with you that intrusion detection systems are needed, that current intrusion detection systems suck, that anomaly detection systems are needed in order to have some useful detection schemes. I tried also to show you some of my research in how to make a better unsupervised learning anomaly detection system based on system call sequences. Currently, this system is not running online, still running offline on batches of logs of evaluation. There's no reason it couldn't run online. Actually, we are integrating it to run online. There's no reason, in fact, that this could not be integrated in an intrusion prevention system of sort. If it behaves as well as I hope it will, it could be integrated, for example, with an intrusion prevention system. Core Force is the one that is ringing in my mind right now, but you may have better suggestions. What we need really, but this is a need that it's not just my need, but it's a need of our research community, is that someone, somewhere, comes up with a good idea on how to test intrusion detection systems. Because until we must rely on 1999 and 1998